It's my great pleasure today to introduce Richard Morey. He did a BA in music initially, and then MA in stats and psychology at Missouri, and a PhD in Missouri with Jeff Rauder, finishing that in 2008. And that's when he developed, that's right, you developed Bayes factor, your basic Bayes factor then in your PhD. Yeah. He went straight from a PhD to assistant and associate professor at Groningen in the Netherlands, before getting the job in Cardiff, senior lecturer in Cardiff, 2015, where they took him on to develop, partly to develop the curriculum, statistics curriculum for psychology undergraduates, to be, not just for Cardiff, but to be a model for everywhere else, which is a task, introducing Bayes into statistics. We need to corrupt the youth when they're young, and then the battle will be won, I believe. So Richard developed the peer reviewers openness initiative, which I signed up to, which is where you say you pledge to not review papers unless the data is transparently, openly available, or a good reason is given why that won't be. And just because of signing that initiative, that I thought, well, I can't really sign this and not make my data available. So that's when I asked my co-authors if they would make all of their data available, which they said they would. So, and that's why a little pledge like that can really make changes. In fact, there's 300 signatories on that, and 4 journals have signed up to it, including discussion with a very high-profile one, which maybe next year will require open data for submission at a journal you'll have all have heard of and probably want to publish in. Richard's development of Bayes has not only deepened my own understanding of Bayes, it's prodded me to develop my thinking further on Bayesian matters. So I regard Richard as one of the forward-thinking people who could be developing the procedures we'll be using in 100 years' time. And on that note,
oh, I hope we move beyond whatever we come up with by 100 years.
maybe we'll see.
Hopefully, we see more progress than we've seen in the past 100. But thank you very much, and thank you for the invitation. So I'm glad to see that there are a number of people here that are interested in confidence intervals, because confidence intervals are not known to be one of those sexy topics that everybody goes out to see talks about, but in the past few years they've been really at the center of the methodological debate that we've been having in psychology and beyond psychology, including medicine and the like. So really understanding what confidence intervals are and what the theory underlying confidence intervals are is really important for how we move forward. So let's talk about confidence intervals. What are confidence intervals? In general, they're a sort of interval estimate. There are lots of different kinds of interval estimates. And the basic idea behind an interval estimate is to take the idea of a point estimate and to work into it some sort of measure of uncertainty, right? Rather than just go with, say, an estimate of the mean that might be 99.3, we want to have some sort of interval around it to express uncertainty in some way, right? There are lots of ways of doing this, but confidence intervals are one way. Now, we can talk about confidence intervals for all kinds of quantities. We can talk about confidence intervals for means, effect sizes, proportion of variance, all kinds of things that you will have encountered. We can talk about interval estimates for. And one of the things that has been consistently suggested as a replacement for significance tests. Because significance tests have come under a lot of fire recently, for the past many decades. And so there have been many people, and I'll talk about some of them today, who have stepped up and said, confidence intervals are the way forward. And they're supposed to be more intuitive, less dichotomous. You have a whole range, and so you don't have this significant or not significant idea. And so, for instance, the APA manual says that estimates of appropriate effect sizes and confidence intervals are the minimum expectations for reporting results. So this is the APA manual. This is a big deal. So now we have to ask, what is a confidence interval in technical terms? So in 1937, Neyman published a big theoretical paper, a classic theoretical paper about confidence intervals. And for the past several years, he had been developing the idea. But to really understand what a confidence interval is, we have to step back and talk about something called a confidence procedure, because this is the foundation of the confidence interval. So what's a confidence procedure? Well, Neyman says we're going to do three things. We're going to sample data from a population, just like we always do. We're going to compute two numbers from the data, which we're going to call L and U. L is a lower bound on an interval, and U is an upper bound, right? So this is an interval. We can talk about confidence sets and these sorts of things, so we don't have to just have an interval. But nothing that I'm going to say is going to need that sort of generalization. And then we do something interesting. This is the key part of the confidence procedure. We say with certainty that the parameter is inside the interval from L to U. That's very important. We just say that statement. It is in that interval. And Neyman would say that we act as if that is true, right? We decide to behave as if that is true. Now, if we go through this procedure and we do it over and over and over again, and this procedure is such that this statement right here is true X% of the time, say 95% of the time, then this is a 95, say, % confidence procedure, right? In 95% of repeated samples, this interval will capture the true value, or this statement will be true. The parameter is inside the interval. That's what a confidence procedure is. Now that we have the idea of a confidence procedure, now we have to decide what a confidence interval is. And it's very easy. A confidence interval is just a realization from a confidence procedure. So we collect some data, we compute that interval, and so we have two fixed numbers now. And we say the true value is inside this interval that we just computed. But this, some problems arise from this of interpretation, right? How do you interpret a specific confidence interval aside from the behavioral choice to say that the interval contains the true value? Well, there have been a number of ways of dealing with this. So some people say that a confidence interval indicates the precision of an estimate of a parameter, right? So you've got wide confidence intervals, you've got narrow confidence intervals, and wide confidence intervals indicate less precision than narrow confidence intervals. Some users of confidence intervals or advocates of confidence intervals also say that the confidence interval contains the likely values of a parameter. Now, I put this in quotes because likely has a technical definition, and the advocates of confidence intervals often slip between the lay definition and the technical definition, and we'll talk about why from a technical perspective this is not necessary. Maybe a confidence interval has an X% probability of containing the true value. That is, the interval that I have just computed, I can say with 95% confidence that that interval contains the true value. These are all ways that people interpret confidence intervals. This talk will be available to you via a link. So I'm not going to read every one of these quotes, but I'm giving some examples here of commentators that have made, that have used these various interpretations of confidence intervals. So here's a precision. Long confidence intervals will soon let us know if our experiment is weak and can give only imprecise estimates. Here is the last interpretation here. The interpretation of the confidence interval constructed around that specific mean would be that there is a 95% probability that the interval is one of the 95% of all possible confidence intervals that includes the population mean. Put more simply, in the absence of other information, there is a 95% probability that the obtained interval includes the population mean. So here, this 95% probability is reflecting some measure of certainty that that particular interval contains the true value. Now remember, with a confidence interval, we made the choice to say that it is inside that interval, and the property that the interval, that the procedure has, is that 95% of the time that will be correct. This is different than what we have here, in which the 95% probability reflects some uncertainty about that judgment. I'm not going to read all of those, but each of these is a fallacy, it turns out. They are not true of confidence intervals in general, in spite of what you may have heard in talks, in spite of what you may have read in your textbooks. They're fallacies. And I've categorized the various fallacies of confidence intervals into three basic fallacies that all the other fallacies are versions of. So the precision fallacy says that the width of a confidence interval indicates the precision of the estimate of a parameter. Narrow confidence intervals indicate precise knowledge, while wide confidence intervals indicate imprecise knowledge. Now, let me be clear about what I'm saying here. I'm not saying that there are no confidence intervals that have this property, because there are. What I'm saying is that this is not a general property of confidence intervals, and it doesn't arise from confidence interval theory at all. You have to justify it in a different way. The likelihood or plausibility fallacy says that the values inside a confidence interval are plausible or likely, or at least more plausible or likely than those outside the confidence interval. And the most important one, from my perspective, is what I call the fundamental confidence fallacy. If a confidence interval was computed from an X% confidence procedure, then the probability that the confidence interval contains the true value is 95%. So notice what we've done here is we've taken the long-run probability of, say, 95% that it captures the true value, and we've turned that into a statement about our certainty that any given, some given confidence interval that we have obtained contains the true value, right? So we've moved from one statement to another. So let's first talk about the fundamental confidence fallacy. Now, I call this the fundamental confidence fallacy because it seems to arise from the very definition of a confidence interval. So what does Neyman have to say about this? He says in his 1937 paper about confidence intervals, consider now the case when a sample is already drawn and the confidence interval is given. Can we say in this particular case that the probability of the true value of the parameter falling between L and U is equal to 1 minus alpha, so say 95%? The answer is obviously in the negative. Now, so Neyman and the frequentists of the period were under no illusions about what the definition of a confidence interval is and what you could infer from it. So the fundamental confidence fallacy did not arise from Neyman saying that a confidence interval was something that it wasn't. It arose later when people started to use confidence intervals, right? So Neyman is saying here, no, that's not what a confidence interval is. That's a fallacy. So if you believe that this is true, don't feel guilty about this. So in a 1937 seminar with Neyman, a young Milton Friedman, this is not a young Milton Friedman, it's an old Milton Friedman, but I'm pretty sure he always looked like this anyway. Young Milton Friedman asks Neyman, your statement of probability that he, that is the user of the confidence interval, will be correct in 99% of the cases is, for a 99% confidence interval, is also equivalent to the statement, is it not, that the probability is 99 out of 100 that the true parameter lies between the limits L and U. And you can almost feel the exasperation from Neyman as he answers Milton Friedman saying, no, this is the point I tried to emphasize in my first two lectures, both in theoretical discussions and in examples, right? So if Milton Friedman can make this error, so can you, it's okay. But this was a confusion that many people had and many people have. And so what I'm going to try to do is show you why this is a problem, why it doesn't actually arise from confidence interval theory, and what confidence interval theory actually says. So let's first start with the really easy way to see that this must be a fallacy. So remember, the fallacy arises because we take the long run probability of the procedure, that is, say, 95%, and we turn it into a statement about our uncertainty in a particular confidence interval, right? So imagine that we draw n equals 10 normal observations with normal variance, or with a known variance, right? So we have normal observations. We're going to draw 10 of them, and we're going to compute a confidence interval. Actually, we're going to compute two confidence intervals. We're going to compute a z interval because we know the variance. So you can go back to your first year statistics course, and you can compute a z interval using the known variance, right? So we're going to use. I should have made this a 50% interval. These values should be different, but we can either compute a z interval, or we can actually use the t confidence interval if we liked, right? I mean, it turns out that we don't want to use the t interval because it's less efficient, but it has the same long-run probability of including the true value. That is 95% in this case. And so all a confidence interval says is that in 95% of repeated samples, I will have captured the true value. Now this is true of both the z interval and the t interval. So as you might imagine from using the knowledge that you have back from first year statistics, you know that the z interval and the t interval are going to be different sizes because one of them uses the true variance, or the true standard deviation, and the other uses the sample standard deviation, right? So if we look at the formula for the interval, here we have the true standard deviation, and here we have the sample standard deviation. So they're going to be different sizes, but they both have the same long-run coverage probability. I can't say that this has a 95% chance of containing the true value, and this also has a 95% chance of containing the true value, without saying that there is no probability that the true value is inside of this region here, right? So by the laws of probability, that's impossible. So they both really can't reasonably have the same probability of containing the true value because they're different sizes, and yet they have the same long-run probability of containing the true value. So there's a contradiction here. We can see the problem, but now the question is, why does this arise? And that's what we're going to talk about. We're going to talk about it in the context of a sort of fun example that I call the missing submarine. The missing submarine is a submarine that we need to find. So you have to imagine that we're sitting on the water in a rescue boat, and we sort of live in this one-dimensional universe where this submarine is at the bottom of an ocean. And we want to find the hatch of the submarine because the submarine has run into some technical trouble. So we know it's down there somewhere. But we want to find that hatch. And we're sitting at the top of the ocean. So this axis here, we're going to call it the location of the submarine. And the submarine is 10 meters wide. And the hatch that we want to find is right in the middle of the submarine. And so we're going to call theta. Theta is a parameter. It's a location parameter. And the submarine goes from theta minus 5 meters all the way to the back, which is theta plus 5 meters. Our goal is to find this hatch right in the middle, which is theta, right? So it turns out we know something interesting about this submarine, and we're going to use this knowledge to try to find the submarine because we don't have any sonar or anything. We know that this submarine lets off very distinctive bubbles, and these bubbles, they occur with uniform probability and independently anywhere on the surface, the top surface of the submarine, and they just rise. And we get to see the bubbles on the surface. So when we see one of these bubbles, we actually get a lot of information from that. The first bubble we see, we know that the hatch of the submarine has to be somewhere within 5 meters of that bubble, right? Because we won't get this distinctive bubble from somewhere else. Now, it actually lets off 2 bubbles, and we're going to use those 2 bubbles in order to find the hatch. So bubbles occur with uniform probability across the surface of this submarine, and we get to see them at the top. They rise up. So the first thing to notice is that these bubbles give us a lot of information, and we can use that to work out the location of the hatch. Now, I just told you, and it's a matter of basic logic, that no bubble can be any further than 5 meters from the hatch, right? Because the end of the submarines are 5 meters from the hatch. So what I can do is I can work out all of the locations that are within 5 meters of the hatch, and those are the possible values that the hatch could be at, right? And I can exclude any location that is more than 5 meters from one of the bubbles. We're going to call that the likelihood. It actually, this white band here represents all the possible values for that hatch. That's all it represents. We've just excluded every impossible value. Anything not marked white here, any location not white, is impossible. Can't have occurred because more than 5 meters from the bubble, or from the it's more than 5 meters from some bubble. So that's what we call the likelihood. So how can we build a 50% confidence interval? I'm going to work with 50% confidence intervals because they make certain things easier. Of course, the confidence coefficient of a confidence interval is sort of arbitrary. It's something you have to choose. But the 50% inside-outside probability is something that makes it easy to work with, so we're going to stick with 50%, with a 50% confidence interval. So I'm going to build 5 different confidence intervals. Now, even at this point, you should start to see some sort of interesting problem. So we saw this with the normal confidence interval, with the fact that we could have a z interval and a t interval, and they both have the same long-run probability of including the true value, and yet they're different widths. Now I've got 5 instead of 2. And now we're going to talk about the properties of these intervals and why one might choose one over the other. I'm going to start with ooh, that's weird. I should have a coin here, but it doesn't seem to be coming up. What we're going to do is we're going to flip a coin. And if it comes up heads, our confidence interval is going to be the whole ocean, right? So every value, our interval is going to be every location. If it comes up tails, then our confidence interval is going to be empty. That is, there are going to be no locations in it. Now you can see right off the bat that this is a silly interval. Nobody would ever use this. So why do I bring it up? I bring it up because this obviously has 50% coverage. That is, when I flip a coin and it comes up heads, and hence my confidence interval is the entire ocean, then I'm definitely going to include the location of the submarine. If it's empty, I'm not, right? So this has 50% coverage. It contains the true value 50% of the time. But it's useless, right? Nobody would ever use this interval. And so coverage by itself is not useful. We need some additional idea in order to tell us which interval we're going to use. So that's what we're going to talk about, because Bayesians and frequentists disagree on what the additional information that we need about a procedure is, or what the additional information that we're going to bring to bear. So here's our first interval that is not completely silly. I'm going to call it the nonparametric interval. And it's really easy. What we're going to do is we're going to take those two bubbles, and because they're independent of one another, and the hatch is right in the middle, what I can say is there's a 25% chance that both bubbles occur on one side of the hatch, and there's a 25% chance that both bubbles occur on the other side of the hatch. So that must mean, by the laws of probability, that there's a 50% chance that they're on opposite sides of the hatch, right? So, actually, 50% of the time, my two bubbles will be on either side of the hatch, right? So the interval between the bubbles, it turns out, is a 50% interval. So this is it works for the median with n equals 2. And this has actually been suggested as a nonparametric interval for the median. Incidentally, and I say incidentally because this is not necessary to my critique, but it gives you a sense that this is not a completely silly interval. It corresponds to the student's t interval if you have n equals 2. If you work it out with your t statistic with n equals 2, you'll find that the interval between your two values turns out to be your 50% confidence interval. So it's not completely silly. It is completely silly, but for a different reason. So how does this nonparametric interval work? Well, you just take your two bubbles. So I put my two bubbles here. Let's say I saw these two bubbles. My confidence interval is just the interval between the two bubbles. That's it. So if I saw these two bubbles, that's my interval. If I saw these two bubbles, that's my interval. Now, I want you to see something important here that is going to come up again, and that is that if I see bubbles like this, what do I know about the hatch? So this is my first attempt at audience engagement. So if I see these two bubbles, do I know a lot about where the hatch is, or do I know a little about where the hatch is? Do I have precise information, or do I have imprecise information?
Precise.
Precise? Yes, why? Why do I have precise information?
You know exactly where it is. Right in the middle of those two.
Yeah, it's got to be right in the middle, basically right in the middle of these two bubbles, because I know my submarine is 10 meters wide, right? So if I get two bubbles that are 10 meters wide, I know the hatch, these two bubbles have to be at the ends of the submarine, right? I have a very wide interval, and yet I have very precise information about the hatch. This is the first clue that something must be going wrong with this interval. So that was the nonparametric interval. Let's talk about a different interval that's actually based on something that may be more familiar with you, familiar for you, the sampling distribution. So probably one of the ways that you were taught how to build a confidence interval is to take the sampling distribution of your statistic. In this case, we can use the mean bubble location as an estimate of the hatch. So we look at x bar, and we work out that sampling distribution. It turns out it looks like this. The sampling distribution for the mean is centered around the true value, and it has this triangular distribution. Why does it have this triangular distribution? Well, remember that we have a uniform, a flat distribution over the bubbles, and this is sort of, I'm taking the average of two bubbles, and so this is one step towards the normal distribution in the central limit theorem, right? We're starting to get something that looks more bell-shaped, right? So that's what's going on here. But I know that this is the distribution. Well, I can work out this distribution, and 50% of the 50% of means that I sample are within 1.6 meters of the true value. So if I have a 50% chance of obtaining a mean that is within 1.6 meters of the true value, then I can use this as what a statistician will call a pivotal quantity, and I can say that my confidence interval is, this here is about 1.6 meters. My confidence interval is x bar plus or minus 1.6 meters. This has a 50% chance of including the true value. Now notice, though, because I knew the sampling distribution up to its shift, the shift of the distribution, which is theta, I knew the variance of this distribution. This is just always going to be the same width, in the same way that your z interval always has the same width for a given n. This is always the same width. So it's just x bar, the mean bubble location, plus or minus 1.6 meters. That has a 50% chance of including the true value. So let's look at and see what this looks like. So here are my two bubbles again. Here's my non-parametric interval, and here's my sampling distribution interval. Notice that it's a bit wider than the non-parametric interval. If I have these bubbles, notice that now my sampling distribution interval is narrower than my non-parametric interval, but it hasn't changed width. It's a fixed width interval. So that's the sampling distribution interval. Now here's my third, or actually my fourth, if you include the trivial interval. The uniformly most powerful interval. Well, one thing that you should have noticed when I talked about the non-parametric interval being having this weird property is that when I have a very wide non-parametric interval, I have very precise knowledge about where the hatch has to be. And so this non-parametric interval actually contains a whole lot of impossible values, right? So I know that the hatch has to be right in here, but and the hatch can't be out here, and yet the non-parametric interval contains that value, right? So that's strange. What am I going to do? What I'm going to do is, when that happens, when my interval contains impossible values, I'm going to truncate that interval so that it only contains possible values. So what I do is I replace the non-parametric interval with the likelihood when I get that impossible, when I get that it includes impossible values. And that actually happens whenever the width of the interval is, the non-parametric interval is greater than 5. It turns out, it's easy to prove. But if you think about this, the likelihood is a 100% confidence interval, right? Because it contains all the possible values and none of the impossible values. So in cases when the width of the non-parametric interval is greater than 5, I'm replacing my non-parametric interval with my likelihood, which is a 100% confidence interval. I know that it has to include the true value. Now, it turns out that in spite of the fact that this has some interesting properties that I just mentioned, it's the inversion of the most powerful test. And this will be important as we talk about properties of confidence intervals. This is the best confidence interval from a frequentist perspective, or from Neyman's frequentist perspective. So here I have my two bubbles again and my non-parametric interval. Now, this non-parametric interval doesn't contain any impossible values because it's relatively narrow. The impossible values only happen when I have a width of greater than 5 on the nonparametric interval. And so my uniformly most powerful interval, or my UMP interval, is the same as the nonparametric interval. Now, because these bubbles are quite close to one another, my likelihood is quite wide. When I have bubbles that are close to one another, I have very little information about where the hatch is, and so my likelihood is wide. Now, when I have two bubbles that are very far from one another, I have a lot of information about where the hatch is, and so my likelihood is very narrow. Now, this nonparametric interval contains a lot of impossible values. Notice anything that's not in this white bar is impossible. The hatch cannot possibly be there. And so my UMP interval is just the likelihood. It just encapsulates all the likelihood, the values that are in the likelihood. Now, like I said, this is interesting because in this case, I know that this 50% interval contains the true value. I'm 100% sure that my 50% interval contains the true value. That seems an odd property for a 50% confidence interval to have, that we're totally sure that it contains the true value. All right, so we can also talk about a Bayesian interval. I'm going to talk about this interval from a Bayesian perspective. You can actually justify it from a fiducial perspective as well. Fiducial statistics is a sort of another logic of inference that was developed by Fisher. I'm not going to talk about that. I'm just going to talk about its justification in terms of Bayes. But it can be justified on other grounds as well. So in Bayesian theory, our inferences are based on posterior distributions. Now, if I combine my likelihood, which is what the data tell me about the possible values of the hatch, with a prior distribution, and actually with Bayes' theorem, I can say that the posterior is proportional to the likelihood times the prior. I just have to multiply two distributions together, essentially, or two different curves. And let's say that the prior is flat. What I get is my likelihood back, right? So if my prior is flat, that is, every value in the range is equally likely, then I'm going to get my likelihood back, and I take half the likelihood for a 50% interval. So that's what I'm going to do. Half the likelihood for a 50% interval. It turns out that this also is a 50% confidence interval. It's what we call a Bayesian credible interval, but it's also a 50% confidence interval. That is, in repeated samples, it will contain the true value 50% of the time. Now that's an interesting fact. So we can actually add this to our confidence, our list of confidence intervals, because it is a confidence interval. This is a sort of graphic that shows what happens. I have a prior distribution, which is flat over all the values in this range, these are my two bubbles, and you can see what I've done is I've shaded every location that is within 5 meters of a particular bubble, and so where those overlap, this dark overlapping region, is the possible locations. These are all the possible locations for that hatch, right? So this is just what we've said before. These are the locations that are within 5 meters of both bubbles. So this is my likelihood here, and so I just take half of that, because this is a posterior distribution, and I take half of it and I get a credible interval. So that's pretty easy. I can do it even if I have an informative prior, if I liked. I'll just end up with a sort of slice of that prior distribution after I've excluded all of the impossible values. You can do that. It's not going to be important for our particular analysis, but it's totally possible. If you use the flat prior, though, you get a confidence interval. So here you can see what I've done is I've put the Bayes interval here corresponding to these two bubbles, and here's my likelihood, and the Bayes interval is just half of it. The middle half. If I have these wide bubbles, then I take half of the likelihood again, and I end up with this very narrow 50% confidence interval or 50% credible interval. So notice now we have these 5 or 4, if we exclude the trivial interval. We have 4 confidence intervals that are all different widths. We have to choose between them. So we have our nonparametric interval, our sampling distribution interval, our UMP interval, our Bayesian interval, and so we have to choose between them. And we need a statistical theory in order to guide our decision. We have to decide what it is we want out of confidence intervals. Now, Frequentist, Neyman's Frequentist confidence interval theory had some guidance for this. What Neyman said is that we actually prefer confidence intervals, or confidence procedures really, that exclude false values at higher rates, right? So we want to include the true value 50% of the time, but we also want to exclude false values as often as possible, right? Because we don't want the case that our confidence interval contains too many wrong values. This is analogous to power, right? This is analogous to the power of a significance test. We also have the idea that we would like to exclude false values. Okay, so which interval are we going to choose? Here, what I've plotted is all of the different alternatives for the location of the hatch. The true value is theta in the middle, and so any value that isn't theta is a wrong value. For instance, here we have the value theta minus 2.5 meters. If we go up from here, we can see the probability that every one of our intervals contains that false value. Now, we want that to be low, right? We don't like to include false values. So every one of these curves represents a different confidence interval. This is the UMP interval here. And you can see that the UMP interval is actually lower than every other curve, right? It's the inversion of the most powerful test. And so it excludes false values better than any other interval in the long run. Now, if you look at this curve here, this is the sampling distribution interval. And you can see that actually the sampling distribution interval is lower than the Bayes interval for the entire range, just like the UMP interval is. So the Bayes interval is worse in all cases than the sampling distribution interval and the UMP interval from a frequentist perspective. It is including false values at higher rates. Now, if we look at the nonparametric interval, you can see that the Bayes interval is better than it for a range of false values and worse than it for another range. So it doesn't completely dominate anything. And here we have our trivial interval. Now remember, our trivial interval is either the whole ocean or nothing. And so it contains all values regardless of whether they're true or false with 50% probability. That's why it's awful, right, from a frequentist perspective. No frequentist would ever use that. But it is a confidence interval. So which interval do we use? Well, we know that the UMP interval is preferred to the Bayes interval and also to all other intervals. And I'm not making this up. Welch in 1939 said that obviously this frequentist interval was preferred to the Bayes interval. The sampling distribution interval is preferred to the Bayes interval. And the Bayes interval is not necessarily preferred to the nonparametric interval, but we do know that the sampling distribution interval is better from a frequentist perspective than the Bayes interval. And so is the UMP. So frequentist confidence interval theory rejects the Bayes interval. No question about it. But let's look at the other properties of the Bayes interval and see how it fares. Well, first of all, we already talked about the fact that The other intervals, this includes the sampling distribution interval, either are 100% confidence interval some of the time, or contain false values, values that we know have to be false, right? So that's already pretty weird, that we can be 100% certain that a 50% confidence interval contains a true value. It's not accounting for our uncertainty in a correct way. But let's look at the relationship of the width of the confidence interval and precision, the precision of our knowledge. I've already hinted at this. On this axis here is the width of the likelihood. Now, when the width of the likelihood is very narrow, that is, that white band is very narrow, we have a lot of knowledge, and so our uncertainty is low. We would expect that the width of the confidence interval is a monotonically increasing function of the uncertainty that we have, right? That the confidence interval, in some sense, quantifies our uncertainty about the parameter, about the location of the hatch. Now, you'll notice that, as I've already pointed out, the nonparametric interval is negatively related with the uncertainty we have. That is, when we have a very wide nonparametric interval, our bubbles are very far apart, we have very certain knowledge about where the hatch is. And the opposite is true, right? So this is weird. Our nonparametric interval is negatively related with the uncertainty we have. The sampling distribution interval has a fixed width, so it's not related at all with the uncertainty we have. The UMP interval is weird because half of the time, when we have very little uncertainty, the UMP interval is the same as the likelihood. So you'll notice that it's above the Bayes interval. That's because it has a 100% chance of including the true value, because it's the whole likelihood. But then when it gets to be when it gets to be wider than 5, the likelihood, that's when it's the same as the nonparametric interval, and so now it's negatively related to the uncertainty, right? So this is strange. The UMP interval is sometimes related in the right way, and sometimes related in the wrong way. That's really odd. The Bayesian interval is the only one that is at all points, at all widths of the likelihood, related positively with the uncertainty that we have. So let's talk about these properties. We can see the precision fallacy because the narrowness of the nonparametric interval is inversely related to the precision. The narrowness of the sampling distribution interval is not related to the precision at all. And the narrowness of the UMP interval is sometimes related to the precision, which is super odd. The likelihood fallacy we can see because the nonparametric interval and the sampling distribution interval can contain mostly impossible values. So we know that those values can't be right, and yet they're still included in the 50% confidence interval. And the 3 non-Bayesian intervals can actually fail to contain reasonable ones because they're too narrow. So relative to the likelihood. The fundamental confidence fallacy is pretty obvious because we can actually have 100% probability or 100% certainty that a 50% interval contains the true value. And when for instance, when one of these, say the nonparametric interval is very wide, that 50% interval can have a nearly, sorry, the other way around. When it's very narrow, it can have a nearly 0% chance of containing the hatch because it's not reflecting the uncertainty that we actually have in our interval. So that's, we can see all 3 of these fallacies at play in this example. And this isn't an accident. It's not that Neyman didn't know that this was the case. In fact, he did. He just thought it was irrelevant. because his particular statistical philosophy was one in which statistics is not about rational belief, right? It was about procedures and coming up with procedures that were optimal in the long run in terms of some sort of behavior that one chooses. So in 1957, Neyman says, statistical inferences are certainly not any sort of reasoning, at least not in the sense in which this word is used in other instances. They're acts of will. And in this case, for the confidence interval, the act of will was deciding to behave as if the interval definitely contained the true value. In terms of confidence intervals, he said in 1941 that it is not suggested that we can conclude that the interval contains theta, nor should we believe that the interval contains theta. Rather, we decide to behave as if we actually knew that the true value was in the interval. This is done as a result of our decision and has nothing to do with reasoning or conclusion. The reasoning ended when the CI procedure was derived. That is, when the math was done before. This is not reasoning from data that we collect. The above process of using confidence intervals is also devoid of any belief concerning the value of theta. Right? So all the stuff that I've just told you is completely consistent with the theory on which confidence intervals are based. So let's talk about the two theories. Frequentist confidence interval theory gives you a single dichotomous decision, that is, it either is or isn't in the interval, with a fixed error rate. You know that you'll be right in, say, 95% of samples. It might give you good average rates of rejecting false values if you are a competent statistician and you know how to derive good confidence intervals. You can have this, and it doesn't give you anything more, right? As Neyman said, it's not about reasoning from data, anything like that. It doesn't give you anything more than that. That's what CI theory gives you, just those things. Bayesian theory, on the other hand, must respect the precision in the data because that's what the likelihood is. It's derived, the posteriors are derived from the likelihood. They can be interpreted in terms of rational belief, like we all think. I think maybe there are exceptions to this, but scientists tend to think of statistics as being about reasoning from data and what we can rationally believe on the basis of the data that we collect. And we can interpret Bayesian statistics with limits that are given by the priors. We can't interpret them that way. And it doesn't impose any dichotomous actions on its users unless they want them. So to conclude, confidence intervals do not, in general, have the properties that people think they do. They don't necessarily say anything about the precision of your knowledge about a parameter. They don't necessarily include plausible values, and they don't necessarily exclude implausible values. And they don't have a, say, 95% probability of including the true value in any given instance. They can, in fact, have a 100% chance of including the true value. There's no reason that a confidence interval needs to be reasonable. And so this is extremely worrying because what you have in the applied statistics literature, let's say you go to psych methods and you look at some papers, you'll see that there is an awful lot of derivation of confidence intervals in which no properties except the coverage is checked. And often that's just checked by simulation. And so people say, okay, this procedure has 95% coverage. And they never check any other properties. So who knows whether these procedures have reasonable values or have reasonable properties? Nobody knows. Now, there are some confidence intervals that are reasonable ones, and they turn out to be the Bayesian ones. And there's a good reason for that. So before you accept the use of any confidence procedure, one that you may have seen in the literature, you should ask about its Bayesian or likelihood as properties, because you have no reason to believe, just on the basis that an interval is a confidence interval, that it says anything reasonable about what you should think about a parameter. And that's all I have. So. Yes.
This is just like a little question. In terms of your use of the word kind of like belief, like
Yep.
rational belief,
Yep.
it seems kind of too strong of a word from like one experiment. Because isn't the idea that like then you want to kind of replicate, so you wouldn't want to call it really a belief?
Yeah, okay, so I'm using belief here in the technical sense in which it's used with Bayesian statistics. So there's a formalization of belief that's related to probability theory. And what you think in a general sense about a particular phenomenon is much more complicated than that, right? So here I'm using it in its Bayesian sense.
Okay, thanks.
You said that confidence interval can make sense on the long run.
Yeah.
Can you elaborate on that?
So, I mean, the definition of a confidence interval is one in which, let me go back to it, we have some procedure that in the long run, that interval in repeated samples will contain the true value some fixed amount of time, right? So if that's your goal, then, and you don't want to say anything reasonable about the values of a parameter in any given circumstance. If your goal is just to make some sort of dichotomous statement like, yes, the true value is in this interval, and you want to be right, say 95% of the time, then a confidence interval will do that. And if you have a good confidence interval, it will exclude false values at some reasonably, at some higher rate than bad confidence intervals will, right?
If you want to apply this line of reasoning to research,
Yeah.
what kind of research approach you should have? That is collective testing of hypotheses with repeated.
I have no idea. That's why I don't advocate confidence intervals, right? It's difficult to think about the usefulness of a procedure that is defined in terms of the long run error rates, rather than one that gives you a sense of whether a particular, whether it's reasonable to think that a particular interval contains the true value, right? That's what I would rather do, is think about what it's reasonable to conclude, right? Confidence intervals don't tell you about that, right? So I can't answer your question because I wouldn't advocate using confidence intervals. Although Neyman said that from his perspective, this is exactly what researchers want to do. I want to, what?
Or should do.
Well, both, right? This is what he advocated, and he said that in his experience, there's a 1977 paper where he says this, in his experience, this is what scientists do want to do, right? They want to think about these long-run procedures, and they want to control their error rates. Now, maybe something has changed since 1977, but I've never met a scientist who wanted to do that. And I want to call this Morey's law. It doesn't matter how strange or bad a particular statistical procedure is, there's always somebody who says, this is what scientists really want to do, right? I've read that on a number of occasions for all kinds of different statistical procedures, some of which are good, some of which are bad. And, but to answer your question, I don't know, because I don't advocate confidence intervals. Yes?
Just go back to the one, I think it's around number 32, where you had all the four curves superimposed, the one with the triangle and the...
Here?
That one.
Yep.
Are they probability distributions?
No. They're they're curves. And probability is on this axis. So if I take, let's say I want to know what the probability is that a particular confidence procedure will exclude, or actually in this case include, the false value that is 2.5 meters above the true value, right? So I just move up from here, and it tells me that roughly 20-ish% of the time, the UMP interval will include that false value. Roughly, let's see if we go to the Bayes interval, roughly 30% of the time, my Bayes interval will include that false value. right? So I want this to be low if I'm a frequentist, because
And now what I was just wondering is whether they should all have the same area, because if they're
well, they can't have the same area. I mean, this is lower. This dominates every other.
They clearly don't. But,
Yeah.
If they were probability distributed, then they would need to have the same
Yeah.
area.
Yeah. Yeah. So it is related. The area is related to the sort of average probability.
And you're right, they are not probability distributions,
Yeah.
so they don't have to.
Yeah. Any other questions?
So I think the take-home message is, well, Richard said don't use confidence intervals, and what you could say is use credibility, in other words, Bayes.
Yeah, so my main take-home message is to understand the methods that you want to use and understand. So my last slide, unfortunately for some reason it didn't show up, but my last slide here is Snow White being offered the poisonous apple from the queen or the witch, and there's a lot of advocacy of various methods out there, and Bayes included, and it's very important to understand the philosophy and theory underlying those methods before you go off and decide to use them, right? Confidence intervals have properties that the advocates of confidence intervals don't know that they have, and they don't have properties that the advocates of confidence intervals think that they have, right? So as we're thinking about what methods we want to use in the future, we really have to know what it is we're getting into. And so if somebody says, okay, I see what you're saying about confidence intervals, but I really do want a procedure that gives me a fixed probability of including the true value. And there are statisticians who even now would say, like Larry Wasserman says, scientists should have coverage. We want to be sure that 95% of our 95% confidence intervals contain the true value. If you say, I like that idea, then that's great. But what I dislike is that advocacy right now is based on lack of knowledge about these procedures. And so know what it is you're getting into if you decide to adopt some sort of procedure, Bayes included.
If you always use a uniform prior, what's the long-run probability that a 95% credibility interval includes the parameter?
It depends on what it is that you are, what parameter you're putting that flat prior on, right? It can be 95%. If it's the mean, then your credible interval will be the same numerically as your confidence interval. So there are cases in which they sort of line up numerically. The normal is one of those cases where everything sort of works out nicely. We haven't, this particular example is an example where they don't work out nicely.
So it's a choice of the underlying distribution that's making the difference?
Not necessarily. So we have an example in the paper that this talk is based on, in which we have normal errors, like in an ANOVA model. Yeah. So everything is Gaussian, everything's behaved nicely. But we're interested in a confidence interval on eta squared, the standardized effect size. And because this is a bounded parameter, things really get weird. Yeah. And so, you can take a look at that example. The credible interval and the confidence interval are not like one another. You can get confidence intervals that are empty. They don't contain any parameter value. And so there are frequentist reasons for this. And so if you like that, you can go with the confidence interval. But from the perspective of somebody who wants a procedure that gives them an interval which contains reasonable values, or that you have, say, 95% confidence that it contains the true value, you don't want to end up having empty intervals. that's a strange thing.
Any other questions? Thanks very much.
The fact that probably statistics is used more as a black magic blanket.
Yeah.
Or as a frost you put on the